August 29, 1907, 5:37 p.m. The Quebec Bridge, spanning the St. Lawrence River, is 11 days away from completion. It will be the longest cantilever bridge in the world. 86 workers are on the structure when it begins to twist. The entire southern span, 19,000 tons of steel, collapses into the river in 15 seconds. 75 men die. September 11, 1916. 9 years later. A new bridge, designed with the lessons of the first failure, is being lifted into place. The center span, the final piece, is being hoisted by cables when one of them snaps. The span drops 150 feet into the river. 13 more men die. This is the story of how engineering ambition, economic pressure, and ignored warnings created the same disaster twice. And why the second time proves something more dangerous than ignorance, the belief that you've learned the lesson when you've only learned part of it. Quebec City, 1900. Canada is building a national identity, and it needs symbols. The Transcontinental Railway is complete. Cities are growing. Industry is expanding. But there's a problem. The St. Lawrence River is nearly a mile wide at Quebec City. Crossing it means a ferry, slow, weather-dependent, expensive. A bridge would change everything. Trade routes. Commerce. National pride. In 1900, the Quebec Bridge Company secures funding for the project. The goal isn't just to build a bridge. It's to build the longest cantilever bridge in the world. Longer than the Forth Bridge in Scotland. Longer than anything in America. The design calls for a main span of 1,800 feet, suspended between two massive cantilever arms extending from each shore. No central support in the river. Just steel, engineering, and ambition. The chief engineer is Theodore Cooper, one of the most respected bridge designers in North America. He's 70 years old. He's built bridges across the Mississippi, the Ohio, the Missouri. He's a legend. But Cooper doesn't live in Quebec. He lives in New York. He oversees the project by mail, blueprints, calculations, reports. He visits the site 3 times in 7 years. Here's the first hidden mechanism, and it runs through both collapses. When you design something to be the biggest or the first, you're not just solving an engineering problem. You're solving a marketing problem. And marketing problems create pressure. Pressure to finish on time. Pressure to stay under budget. Pressure to prove it can be done. That pressure doesn't show up in the blueprints, but it shapes every decision. In 1903, the Quebec Bridge Company runs into financial trouble. Construction is slower than expected. Costs are rising. Investors are nervous. So they make a decision. They increase the span length from 1,600 feet to 1,800 feet. Why? Because a longer span means fewer piers, less material in the river, lower costs. But here's the problem. The bridge was already designed. The calculations were done. The steel was ordered. Changing the span length means recalculating the load on every beam, every joint, every connection. It means more weight, more stress, more risk. Theodore Cooper approves the change. He recalculates some of the loads, but not all of them. He trusts the original design. He trusts his experience. And he's under pressure. The company needs the bridge finished. Delays mean more cost. More cost means project failure. So the work continues. By the summer of 1907, the bridge is nearly complete. The southern cantilever arm extends 600 feet over the river. Workers are installing the final sections of the suspended span. But there's a problem. In late August, workers notice something. The lower chord members, massive steel beams running along the bottom of the bridge, are bending. Not much, just a few inches. But they weren't bent before. On August 27, the on-site engineer, Norman McClure, measures the deflection. It's getting worse. He reports it to his supervisor, Peter Slapka, the chief engineer on site. Slapka is concerned, but not alarmed. Bridges flex under load. That's normal. He sends a report to Theodore Cooper in New York. On August 29, Cooper receives the report. He immediately sends a telegram back. Add no more load to bridge until after due consideration of facts. But the telegram arrives at the bridge site at 5:55 p.m. The bridge collapses at 5:37 p.m. Here's what happened. The lower chord members weren't just bending. They were buckling, collapsing under compression. The steel beams were designed to handle a certain load. But the load was greater than calculated. Why? Because when the span was lengthened in 1903, the weight of the bridge increased. And the calculations didn't fully account for it. Specifically, the lower chord members were undersized by 20%. They were carrying 20% more load than they were designed for. For 4 years, the bridge held. But as construction added more weight to the cantilevered section, the stress increased. By August 1907, the beams reached their breaking point. At 5:37 p.m., one beam buckled. The failure propagated in seconds. The entire southern arm, 19,000 tons, twisted, collapsed, and fell into the river. 75 men died. Most were Mohawk ironworkers from the Conowick Reserve near Montreal, men who specialized in high steel work, building skyscrapers and bridges across North America. The collapse made international news. It was the worst bridge disaster in history. The Canadian government launches an investigation. The Royal Commission of Inquiry spends months analyzing the wreckage, reviewing calculations, interviewing engineers. Their conclusion? The bridge failed due to errors in design and calculation. Specifically, the lower chord members were underdesigned. Theodore Cooper, as chief engineer, is found professionally responsible. The report makes recommendations. Increase safety factors. Require independent review of calculations. Ensure on-site supervision by qualified engineers. The report is thorough. It's detailed. It identifies the technical failure. But here's what it doesn't say. It doesn't address the system that allowed the failure. It doesn't ask why Cooper was allowed to oversee the project from 400 miles away. It doesn't ask why the company approved a span change without a full recalculation. It doesn't ask why economic pressure was prioritized over engineering caution. It identifies what broke, but not why it was allowed to break. And that's the midpoint twist. Because 9 years later, the same system produces the same result. 1916, the Quebec Bridge is being rebuilt. New engineers. New design. Stronger steel. Wider safety margins. The lessons of 1907 are applied to the technical design. The calculations are checked. The beams are oversized. Independent reviewers approve the plans. But the economic pressure? Still there. The project is years behind schedule. Costs have tripled. The Canadian government is funding it directly now, and they want it finished. By September 1916, the bridge is nearly complete. The 2 cantilever arms extend from each shore. The final step is to lift the center span, a 5,000-ton steel section, and connect it between the arms. The span is built on a barge in the river. The plan is to float it into position, then lift it using cables and hoists mounted on the cantilever arms. On September 11th, the lift begins. The span rises slowly. 10 feet, 20 feet, 30 feet. Everything is going as planned. Then, at 50 feet above the water, one of the lifting castings fails. A corner bearing, a steel piece connecting the lifting cable to the span, fractures. The span tilts. The weight shifts. Another casting fails, then another. The entire 5,000-ton span drops 150 feet into the river. 13 workers die. So what happened? The castings were designed to handle the weight of the span. But they weren't designed for dynamic load, the stress created by movement during the lift. And there's another problem. The castings were made by a different manufacturer than originally specified. The replacement castings were slightly weaker. But they were approved anyway, because the project was behind schedule, and waiting for the original manufacturer would mean more delays. Economic pressure. Again. Here's the detail that makes this collapse devastating. 3 engineers raised concerns about the castings 2 weeks before the lift. They questioned whether the replacements met the specifications. They asked for testing. The project manager overruled them. Testing would take time. Time meant money. So the lift proceeded. Let's be clear about what this means. The second collapse wasn't a repeat of the first failure. The bridge design was sound. The steel was strong. The calculations were correct. The second collapse was a process failure. A decision-making failure. A failure to prioritize safety over schedule. And that's the misconception worth correcting. People remember the Quebec Bridge as an engineering failure. It's taught in engineering schools as a lesson in structural design. But it's not an engineering failure. It's a systems failure. The first collapse happened because calculations were wrong under pressure. The second collapse happened because warnings were ignored under pressure. The investigation after 1907 fixed the calculations. It didn't fix the pressure. So what do we learn from the Quebec Bridge? Lesson 1. Fixing what broke isn't the same as fixing why it broke. After 1907, the engineers recalculated the loads. They strengthened the beams. They applied the technical lessons. But they didn't change the system that prioritized speed and cost over caution. So in 1916, the same system produced a different failure. Different technical cause, same root cause. This applies beyond bridges. Every time a system fails and you only fix the visible problem, you're setting up the next failure. The question isn't just what went wrong. It's what allowed it to go wrong. Lesson 2. Economic pressure doesn't care about lessons learned. In 1916, the pressure to finish the bridge was higher than in 1907. 9 years of delays. Triple the cost. National embarrassment. That pressure didn't go away because there was a disaster. It got worse. And when pressure increases, shortcuts return. Different shortcuts, but shortcuts. The castings in 1916 weren't weaker because of ignorance. They were weaker because someone made a trade-off, time versus safety. And pressure made that trade-off seem reasonable. This is why lessons learned documents don't prevent repeat failures. Because the lesson isn't about what happened. It's about resisting the pressure that makes it happen again. Lesson 3. You can learn the wrong lesson from a disaster. The 1907 investigation concluded that the bridge failed because of calculation errors. That's true. But it's incomplete. The bridge failed because calculation errors were approved without independent review, because the chief engineer was remote, because the company changed the design to save money, because workers were pressured to continue despite visible warning signs. Fixing the calculations is easy. Fixing the system is hard. And when you think you've learned the lesson but you've only learned part of it, you're more dangerous than if you'd learned nothing. Because now you're confident. And confidence under the same broken system produces the same result. The Quebec Bridge was finally completed in 1917. A third attempt. New lifting system. New procedures. New oversight. It's still standing today. 108 years later. It's still the longest cantilever bridge in the world. 88 people died building it. 75 in the first collapse. 13 in the second. The bridge is a UNESCO World Heritage Site now. It's a symbol of Canadian engineering achievement. But it's also a monument to something else. The difference between learning and learning deeply. Between fixing symptoms and fixing systems. Between asking what broke and asking what let it break. There's a phrase in engineering. Fail-safe design. It means building systems that don't catastrophically collapse when one part fails. But fail-safe design isn't just technical. It's cultural. It's building a system where someone can say stop and be heard. Where warnings are taken seriously even when they're inconvenient. Where pressure to finish doesn't override evidence that something's wrong. The Quebec Bridge had fail-safe steel in 1916. But it didn't have fail-safe culture. And that's the file that matters. That's the story the river still holds. I'll see you in the next one.